Okay, so here we try to introduce the third fundamental circuit component called the inductors. Okay, so actually there are resistor, capacitor, and also inductor here. Okay, so we have learned resistor in chapter 26, and then capacitor in chapter 25, and here is the inductor. Chapter 30. Okay, so these are the fundamental circuit component. Which are linear. Okay, which are linear. Okay, at least it has a linear model. It doesn't. Okay, practically it is not that linear, but at least we have quite well-developed linear model for this kind of component. So after finishing this chapter, I will supplement the, some mathematics about how to solve the constant coefficient linear ODE. Okay, so this is about the so using the differential equation to describing the linear system. In this case, is a RLC circuit. So in that case, the ODE is also linear. So here, so let's come back to here. So it says an inductor is a device that can be used to produce a known B field in a specific region. Okay, so actually it is. You can consider it is the same as the solenoid that we have studied in chapter 29. Okay, so if a current I is established through each of the n windings, okay, so n turns, okay, of an inductor, a magnetic flux phi b links those windings. The inductance of the inductor is L equals. So this is somehow like a definition. Okay, so a definition. So for the resistor, it is like V equals IR, the Ohm's law. I would say that this is somehow like the definition, or actually it's it should be called the Ohm's law, but yeah, I will consider it's like the definition of the resistance. And for the capacitor, Q equals CV is also the definition for the capacitance itself. And this one is somehow like the definition of the inductance. So L is the inductance, and then capital N is the number of turns. Okay, so I have emphasis that capital N and small n are different. Small n are the turn density, okay, or the number of turns per unit length. And here, capital N is the number of turns itself. And then phi b is the magnetic flux, and then normalized by the current. And actually the SI unit for the inductance is called Henry, H. Okay, so actually when we record the B field generated by a solenoid, okay, actually it is something like mu0 IN. Okay, actually this B field is proportional to the current. Okay, so actually here we try to normalize this thing by I. Okay, so it is somehow like B over I is actually mu0 n. Okay, actually this is a constant. This is only related to the geometric shape of the inductance, whether it is dense or not. Okay, so actually the phi b is of course proportional to the B field itself, and also the cross section area, also related to the geometric shape. So actually this thing is only related to the to the geometric shape, okay, not by the inductor. Of course, not by the current. Of course, the current can change the B field and also the magnetic flux generated, and also the number of turn is also the geometric shape. Okay, so this is the definition for the inductance. That's how large is the B field you can generate. Okay, so for the bottom right part, it says the crude inductance, okay, with which microfaraday discovered the law of induction. In those days, entities such as insulated wire, okay, 就是一些绝缘的导线, okay, were not commercially available. Okay, so it is said that Faraday insulated his wire by wrapping them with a strip cut from one of his wife's petticoats. 就是说，那个时候应该是工业上没有办法造出一些绝缘的导线，所以，但是你绕线圈的话，你可能就是那个线不可能互相触碰到啊，所以的话，他就是自己剪他老婆的外衣去裹，现在的话是不可想象。Okay, so actually, so here we come up with some formula. So actually, this is N phi B. So the magnetic flux for N turns. Okay, so it is actually N is of course the density. Okay, the turn density multiplied by the length of the inductor. Okay, the length of the inductor. So N is the number of turn per unit length, the turn density, and actually L. Okay, L should be the length of the inductor. Length of the inductor. Okay, so nothing special here. So here we try to plug in this thing into here. Okay, this is N phi B, so we plug in this one there. So L equals N phi B over I, and then we have NLBA. Okay, NLBA. Phi B is actually BA. We just assume the B field are parallel to or in the same direction as the reactor, so and then B field is approximately to be a uniform inside the solenoid. So we have the phi B to be a surface integral, and then turns out to be a multiplication. So here we have an NLBA over I, and then this is a solenoid just as what I mentioned. So B equals mu 0 IN, and then here we try to move this L to the left hand side. So left hand side will be capital L over L, so the inductance per unit length. And then for the right side, we have N square here, we have mu 0, and then I and I cancel. So here we have I and I cancel, so we have N square and then A, and then mu 0. So this is the inductance per unit length. So it is this one is a constant, and then this is related to the density. Okay, the square of the density. So if it is denser, so the inductance per unit length is also larger. And then if it is has a larger cross section area, the inductance per unit length is also larger. So yeah, so you can expect the coil is can be big if you need a large inductance. And of course, rather than making it denser or making it have a larger cross section area, you can also make it longer so that the total inductance is also larger. Okay, so here we have a phenomenon called a self-induction. Okay, so self-induction. So here, if two coils, which we can now call inductors, are near each other. Okay, so actually, if we assume an inductor with more than one turn, 2 turns or more than 2 turns are also okay. So here with simple setup. So actually, this is a single loop circuit, and then we have a battery here. So generate some potential difference. And then this is a resistor, but this is, you can see this tip here means it is a tunable resistance. Tunable resistor, okay. Tunable resistor. Which means that if this tip is sliding to the right side, the resistance is larger. It's like it should go through it, okay, like this. If it is in the middle, it will be like that. If the tip is here, then it should go through the whole resistance. So the resistance is larger. If the tip all the way goes to the left side, the current go this way. Okay, just give through this whole part, so the resistance will be smaller. So in that case, this is a tunable resistor. So this tube can be, of course, it is just a demonstration. No, it's not that. Yeah, the practical is not necessarily like that. But the idea is you can just try to adjusting the contact point so that you can adjust the resistance. And then of course we have our main role, okay, the inductor in series, okay, in series with the tunable resistor. Okay, so the idea here is we can actually control the current going through the inductor. Okay, so in that case, if we want this I to be larger, then we try to move the tip to the left side, making the resistance to be smaller. So in that case, this case R is smaller, and then the I will be larger. Okay. If it is to the right side, R will be larger, and then I will be smaller. So this tunable resistor is just to adjust the current. Okay, so we have seen that if we change this flux, okay, so which means that if we can change the current, we can change the flux, because the flux is actually the flux, okay, the flux is actually proportional to the B field it generates, and then the B field is actually mu0 In for the solenoid. Okay, so actually this so this B is also proportional. Okay. Is also proportional to the current. So if we can adjust the current, we can actually adjust the flux itself. Okay, so actually if we can change the flux according to Faraday's law, so actually every single coil it can generate B field. So here we try to consider, of course all the coil, all the turn will generate B field. But every time we just try to look at a single turn, it generates some B field, so that for other turns, there will be magnetic flux changes. Okay, if we can actually adjust the current. So for every single turn, it will generate B field. So for other turns, it will have flux changes. And actually, other turns can also generate B field, and then it will also generate the B field to this turn. Okay, so but we want to make it simple. So every time we just consider a single turn, and then it generates some B field for other turns, so that it has flux changes. And in that case, according to the Faraday's law and also the Lenz's law, okay, you can actually consider. So actually for the first turn, let me draw it better. So this is the first turn. okay, with this current. So according to the right hand rule, your forefinger is like this direction, and then your thumb is pointing downwards. So here we just assume that at this moment the eye is in this direction, so it's trying to generate some current, try to generate some B field pointing downward. If it is actually start from 0 and then increasing, so according to the Lenz's law, the other turns will try to generate some B induced. Okay, so B is from the turn 1. Okay, and then for other turns, they try to generate some B induced pointing the opposite side, because here we assume that I is pointing downward, is increasing. Okay, so this I is increasing at this case. Okay, so if it is I is increasing at this case, the B induced will be like pointing upward, and then using right hand rule, the induced current will be like in the opposite direction to the I, so that I induced will be like pointing to the opposite direction to the original current, and then cancel part of the current. So that in that sense, if you just look at the inductor from outside, just say you try to, let's say, consider you have a voltmeter to measure the potential difference across these two nodes. Okay, it will be like there is a voltage drop or the potential drop across the inductor. So that's the self-induction. So here it says, we have seen that if the change the flux by changing the current, and induced EMF appears in the second coil according to the Faraday's law, just as what I mentioned, and induced EMF appears in the first coil as well. This process is called self-induction. So which means that it is actually the same inductor, but it has multiple coils, so it will have self-induction that actually it also even only with only one turn, okay, it will have self-induction for its own turn. Okay, so an induced EMF appears in the first coil as well. So this process is called self-induction, and then the EMF that appears is called the self-induced EMF, and then it will be like have an opposite direction to the current. It obeys Faraday's law of induction just as other induced EMF do. Okay, so if the current doesn't change at all, if it is like the I is constant, then there won't be any magnetic flux change, so there won't be any induced EMF. So the inductor will be like a single wire. Okay, it won't generate B field, it won't generate induced EMF. So I mean, for the steady state, okay, which means that if we just don't change the current at all, okay, making it a constant, so finally it will settle to a value, and then the inductor will look like, for the steady state, the inductor is short. Okay, it's short. Short means zero potential difference. Zero potential difference across it. Okay, there won't be any voltage drop, or in other words. Okay. But for the capacitor, if it is like a steady state, it is like an open circuit. So it is the opposite to the inductor and the capacitor is somehow like the opposite to each other. So in chapter 31, we will also learn the phasor. So it will be like the impedance of them will be, one of it will be a positive imaginary number, one of it will be a negative imaginary number. Okay, so they are somehow like opposite to each other. So in if it is in a time domain, if it is in steady state, L will be like a short circuit for the steady state, but for the capacitor it will be like an open circuit. We will see more about that later on. Okay, so here we try to consider. Okay, so this is the original definition. Okay, if you still remember that equation is something like this. Okay, a few page before. Okay, so we try to move L to the left side and then swapping left and right. So we have N phi B equals Li, and then we try to take derivative on both sides. So we try to take d dt on both sides, and then also we try to take a minus sign for both sides. Okay, so it doesn't change anything. Okay, both sides try to take the derivative with respect to time, and also take the multiply by -1. So according to Faraday's law, this thing is like the Faraday's law is like the induced EMF, and then on the right side will be like, okay, so the left side will be like this, and then for the right side, negative dt Li. Okay, L is not changed with time, so L is like a constant, so negative L di dt. Okay, something like this. Okay, so it's something like this. Okay, so this is actually a useful equation, and to be honest, I seldom use this one. Okay, almost or I'll say before teaching this course, I only know this. Okay, VL equals L di dt. Actually, you will use this one in chapter 27 or chapter 31 later on. So actually, what I use is always like this. Okay, so because for us, we try to use it in the circuit theory. Okay, the circuit theory seldom talk about the E field, B field. They try to make it like all the way using voltage, or what you understand is the potential. Okay, electric potential difference. Okay, the voltage difference and the current. So it will be like the voltage drop for the inductance. Okay, just as what I mentioned, it will have a voltage drop. Will be like this, L times di dt. Okay, so here let me try to summarize it. Okay, so here we have several components. Okay, we have R, we have a C, we have L. Okay, in different chapter. Okay, so actually, you need to slightly pay attention. Okay, because the formula is like V equals IR, and then for the C is I equals C dV dt, and then for the L is V equals L di dt. Okay, something like this. This is C, and then this is L. Okay, so of course there are three formulas, but you need to pay attention to the direction of the current. Yeah, otherwise, even though you know this formula, but you may have an additional minus sign somehow. Okay, so you need to pay attention that, okay, so for the V is in this direction, the I is from the positive to negative across this resistor. Similarly for this, okay, V is like this, and then the I is also in this direction. And then for the inductor, also like this. Okay, so they are consistent to each other, so that you don't need to remember all this case is for resistor, this case for capacitor. So all of them, they have a same figure. Okay, the only difference is the component is different. And then as long as they have the same topology, okay, I would say it has the same topology. You only change the resistor to a capacitor to an inductor, and then they should have different different characteristic, okay, governed by these three equations. Of course, the resistor is the most easiest one, okay. It won't have any derivative, not related to the calculus at all. So it is just an Ohm's law. Even high school students should be able to use it to calculate something, okay. Okay, so this is a resistor. And then for the capacitor, okay, you may say, okay, I have not talked about that before, okay, but actually you have learned that, okay, Q equals C times V. So if we try to take the derivative on both sides, okay, dq dt will be the current, okay, dq dt is current, is a definition. And then on the right side, okay, d dt, the derivative with respect to time for the C times V. C is a constant, just like the inductor is constant, resistor is constant. So we just put C outside, okay, so we have a dv dt. So this is I equals C dv dt. So you can see I equals C dv dt. And then for the inductor, just as what I mentioned here, I will consider, okay, so this is the EMF, okay, so for the circuit theory, we don't like the concept of EMF, okay, so we still use the concept of the potential difference. So in that case, yeah, but actually they are referring to the same thing, okay, it is like this potential is somehow higher than that one, okay, but yeah, so you can consider VL and EL. Just take a opposite sign, okay, so one is positive, one is negative. So here the opposite side, okay, so there is an additional minus sign, so that, yeah, minus times minus becomes positive. Yeah, so so this is the case. And then you can also see it here, this I and this I mean the V and C relationship for the C and L are also like they are somehow like duality, okay, so replacing C and L, you just exchange V and I, okay, exchange V and I. So they somehow they are like opposite to each other somehow. Actually, we will use these three, okay, of course these are the three fundamental circuit components. So we will actually use these three formulas in chapter 27, chapter 31, okay, to do more calculation later on. Okay, so this is one of the part because I have not supplemented the how to solve the constant coefficient ODE yet. Okay, so we just believe it is true. I will let you know, or we'll come back here to let you know. Okay, this is how this formula can be derived. Okay. Maybe 1 or 2 weeks later, okay. So so far just believe it is true, and of course it is true. So here is the RL circuit, so almost the most simple circuit. The most simple circuit will be like this, okay, with only a resistor, only a capacitor, or only an inductor. But this circuit is too simple, okay, so it cannot be used for too many purposes. So here it is a more complicated circuit, slightly more complicated circuit. It has one resistor and one inductor in series, okay. So here we have a battery, we have a resistor, and then an inductor all in series. So we assume that, okay, at the very beginning we don't have any current. Or you can imagine there is a switch here. There is a switch here. There is a switch here at t equals 0. It tries to short. Okay, it tries to close the circuit, so that the current will be like this. Okay, it is somehow it looks complicated, but actually not. Let me try to tell you how we can understand this one. Okay, it's not that complicated. You can actually substitute a few points so that you can have some idea. So for t equals 0, okay, for t equals 0, t equals 0, exponential to 0 is 1, okay, exponential to 0 is 1. So 1 minus 1 is 0. So it turns out that I will be 0, which is this point, And then another point will be like t equals infinity, okay, infinite far away from now. So exponential to negative infinity. What is it? Oh, exponential to infinity, positive infinity will be like infinity. So exponential to negative infinity will be like 0, okay? So 1 minus 0 will be 1. So this I will be E over R, okay? So we will call it a steady state. We will call it a steady state. After sufficient long time later, it is like a steady state. It must be a steady state sometime later. Okay, so and actually this is this point. Of course, this is V out, but actually V out and I is actually proportional to each other, so that I with a unit of A is also looking like this. It's just has a different scale. So this is nothing but E over R for this point, for the I, okay, for the I axis, okay. So yes, so it's somehow like this, and then this is exponentially decay. Okay, I will say this is exponentially decay because this one starting from here is 1 at the beginning and then finally 0, so that it will be like becoming smaller and smaller, So we will say this is a first order exponential decay. Okay, we will usually say that this is exponentially decay. 指数衰减. Okay, so somehow like that. And here we have come up with something called tau L. Tau L is called the inductive time constant. L over R. Its SI unit is S. Okay, second. Okay, of course it's as time. Okay, it is time. So what is this time? This time is actually like if t equals tau L. If t equals tau L means that t equals tau L. This is negative tau L over tau L, negative 1, e to negative 1. 1 minus e to negative 1, and then multiplied by ER, okay, something like this. Okay, so E, you know E is 2.718 281828 or something like that. Okay, so E equals 2.718, something like this. Okay, and actually 1 over E is like 0.3 something. Okay, 0.3 something. So 1 minus 0.3 something is 0.6 something. Okay, which means that it is somewhere here. Okay, so this is actually the tau L. Okay, so this is a point like that. Okay, so actually, how do we determine or what is a steady state? We cannot wait until infinitely long away from now, because we have limited life. So in that case, we, as an engineer, we will try to approximate the steady state to be like if t is larger than, let's say, 5 times tau L, 5 times tau L, then it is almost settled. Why is it like that? Of course, sometimes we can also divide a 3 times time constant, but 5 constant is more safer, and then it is not that long. You can imagine 1 minus e to the negative 5 is really small. Okay, I don't know how small it is. I think it should be like less than 0.01. Okay, I'm not sure. but should be like less than 0.01. So which means that 1 minus e to the negative 5 will be like larger than 0.99. Okay, so we will say that it is 99% settled. Okay, so for most of the case, it will be acceptable for an engineer. Yeah, because even for the noise, it can be quite large, maybe larger than 1%. So if it can be settled, yeah. So which means that if this point is the tau, okay, this point is around the around the 5 tau, okay. So you can imagine, okay, so this one we can consider this is 5 tau L. So it is you can consider it is so close to E over L. It will settle to the E over L, not overpass it, okay, not overshoot it. Yeah, because this one will if this exponent is like, yeah, actually for the exponent exponential function, okay, this thing can be a positive value if the exponent is a real number, okay. It can only be a positive value. So this one is also always like 1 minus something, okay. It cannot go through 1, okay. It cannot go through 1. Okay, so we will come back later so that we will understand why this is correct. But here we try to have a simple sample problem. Okay, so so for the figure, A shows a circuit that contains 3 identical resistors. So here we have identical resistor 1, 2, and 3, all with the same value R equals 9 ohm, 2 identical inductor. So these are the 2 identical inductor with inductance L equals 2 mH, and then an ideal battery EMF to be 18 volt. So what is the current I through the battery just after the switch is closed? Just after the switch is closed. Just after the switch is closed, or maybe I use capital I here. Okay, it doesn't really matter. Although most of the time I use small letter. Yeah, maybe just a typo there. But I don't think it really matters. Okay. So actually, okay, I want to say something more about the capacitor and the inductor. Okay, so here, as much as we have the derivative on the right side, okay, derivative on the right side, which means that V is continuous. V is continuous. For the inductor, I is continuous. Okay. But for the V, not necessary. Okay, for the capacitor, I is not necessary to be continuous, of course. I mean, yeah, because when you learn the calculus, you know that, okay, if you need this to be differentiable, okay, so this thing should be differentiable, okay, so differentiable is strengthened than continuous, but practically, okay, V is only necessary to be continuous, I is only necessary to be continuous. Okay, if it is continuous but not differentiable, it will be something like, okay, I is not continuous at that point. If V is differentiable, if V is really differentiable, then I is continuous. But sometimes V is not, maybe for C, V is not necessary to be differentiable, but V at least to be continuous. Otherwise, if V is not continuous, the derivative will be like infinity large. Okay, and so as for the inductor, okay, I must be continuous so that Yeah, so that V may not be continuous at that point if it is not differentiable, okay? But at very least, for the capacitor, V is continuous. For the inductor, I is continuous. For the R, I and V, not necessary to be continuous, okay? It can be, has quite a lot of jump. Okay, so if you know that, here we will make use of the current. The current of the inductor is continuous because at the very beginning, at t equals 0, it is closed. So which means that before t is 0, there won't be any current going through, and then there won't be any current going through all this element, which means that for the IL, okay, IL, let's say this is IL1, okay, this is IL2 here. Okay, so IL1 T equals IL2 T equals 0 for T is smaller than 0. Okay, so and as much as T is continuous, I mean the current is continuous, which means that IL1 0 plus equals IL2 0 plus is also 0 for T is, for T equals 0 plus second, okay, something like this, okay, something like this. Okay, so which means that what is the current I through the battery just after? Just after means T equals 0 plus second, okay, so the switch is closed. Okay, so in that case, so when the switch is closed, okay, when the switch is closed is something like this, okay, so there will be some current, but for the IL1 path and IL2 path, it should be 0 when T is 0 plus, okay, so which means that there should only be current going through the resistor, okay, and so as this path, okay, all the current will go to this way, okay, so I will be like E over R only, okay, so this one should be open, this one should be open also. There won't be current because the current for the inductor is continuous. So if there is no current going through the inductor at 0 plus, okay, so there won't be current going through the resistor series with it either, okay. So only one resistor can have current going through. So in that case, you can see E is 18 and then R is 9, so this is 2A. So you can see that the current for the resistor is not continuous because for T equals 0 minus, okay, the current going through the resistor is 0, but for T equals 0 plus, okay, the current going through this middle resistor is 2A, okay, so this is not continuous. Okay, for the question B, what is the current I through the battery long after, which means that T is infinity. For T is infinity, the VL infinity will be 0 volt, just as what I mentioned here. The zero potential difference across it. Steady state, okay. For the steady state, L is short, okay. Zero potential difference across it. Or you can consider it here, okay. Consider it here. So I will be 0. So V will also be 0. Okay, so in that case, VL over the inductor will be 0, so it will be looking like this is a short circuit, this is also a short circuit when T tends to infinity. Okay, T tends to infinity. So in that case, this is like R parallel with R parallel with R. Okay, so the circuit actually look like this. One R and other R and then another R, something like this. So this is nothing but R over 3. Okay, so this is the R equivalent. Okay, like this. So finally, I will be like E over R equivalent, which is E over R over 3, which is 3E over R, which is 3 times 18 over 9, which is 6A. So for the steady state, the current is larger. Yeah, because there will be current going through the inductor, and then there is no voltage drop or potential difference across the inductor when t tends to infinity. T tends to infinity. Okay, for infinity, okay, yeah, maybe more rigorous to write it as t tends to infinity rather than t equals infinity. Okay, so yeah, so maybe